Hello everyone. Welcome to this NPTEL course on Mathematical Foundations of Generative AI. In this particular course, we will be focusing on the mathematical nuances and the underpinnings of all the generative modeling algorithms that power today's AI world. Now, as all of you know, artificial intelligence, specifically the generative part of it, has revolutionized the way science and engineering is done. So, we are now immersed with algorithms that are fueled by the generative modeling paradigm. We cannot now imagine a life without the generative AI. So, take for example the algorithms that we interact with on a daily basis, or the systems that we interact with on a daily basis, such as the GPTs and Geminis and Claudes and so on. All of these are examples of systems that are built using the generative AI. So this is a significant paradigm shift that has happened over the last decade in the field of machine learning. What was a dream during the last decade has now become a reality. So, what was a science fiction the last decade has now become reality, where machines can actually think, interact, and solve problems for us. All these capabilities are possible because we use specific types of algorithmic design combined with massive amounts of data and good training paradigm that have made all these algorithms a possibility. So now there are multiple sources of content that is out there that would teach you the way these algorithms are built, these algorithms are used, and so on. But this course, I have designed it with a unique objective that if there is somebody who is interested in not only taking the algorithms off the shelf and using it for their particular use case, but to understand what is happening under the hood and even come up with newer algorithms that would create new possibilities or solve the existing problems in the current ecosystem, then knowing the mathematical details of these algorithms becomes an unavoidable necessity. Now, most of these algorithms are designed by mathematicians and engineers who could think from the mathematical first principles and then use those mathematical tooling to envisage new ways of doing things. So now with that preface, I designed this course in a way where we look at the mathematical nuances of a broad family of generative models, the state-of-the-art generative models, so that somebody who completes this course will be equipped with the mathematical arsenal that is needed to either understand the details of the existing algorithms or to even create new generative algorithms using those tooling. So with that as the gentle introduction, in the first couple of lectures, we will look at some of the foundational mathematical tools that are needed upon which generative modeling, or rather machine learning, is constructed, and that happens to be the probability and statistical toolkit. Now I will just give a broad overview of how one would look at the problem of machine learning in general and generative modeling in particular from the lens of probabilistic models, and then I will talk about the general recipe that is used in most of the generative models in constructing the algorithms that they use. So that is what we are going to do in the first few lectures. So, and then moving forward, we will look at several classes of generative models. So let us discuss about those classes of generative models that we will be covering in this particular course broadly. I'll just take the topic name. So the first, and the style of this course, the teaching style of this course will be the old school way of chalk and talk, where I'll be writing down all the equations that we derive. So we start from the first principles, and then I derive all the underlying equations, and I write down each and every equation that I talk about, but not use a pre-constructed set of slides. And then we'll build everything from first principles. That's the methodology which I've adopted to teach this course. And this course will also have a practical component which will be dealt with by my teaching assistant Chandan. So he will be walking you through all the programmatic or implementation details of all the algorithms that we will be studying in the lecture part of it. So there will be accompanying tutorials for each of the lecture content that we do, so that every algorithm that we study in the lecture part will be implemented practically using the frameworks such as PyTorch that are built on Python, so that a student would understand how to translate all the mathematical constructs that we have discussed in the lecture part into algorithms that can be used in the real world via implementations. Now, broadly, I will start the course with an introduction to probabilistic machine learning. And then we will go to variational methods. Variational methods that are built upon this idea called latent variable modeling. Under these variational methods, there will be multiple algorithms that we will be looking at. One, we start with the mixture models. Mixture models, an example would be the classical Gaussian mixture model, which is one of the classical algorithms that are used for generative modeling. We will also look at the variational autoencoder family. Which are abbreviated as VAEs. Then under the variational methods, we will also look at these family of models called the diffusion models, sometimes also called as DDPMs, denoising diffusion probabilistic models. And then we will look at the adversarial family of models, of which the generative adversarial network, which are also referred to as GANs. This was one of the early and classical, or rather early methods in the neural family of generative models that created a lot of buzz around the world. And then we will look at the autoregressive family of models, autoregressive models. Within autoregressive models, you have the transformer based LLMs that we see today, transformer based language models, or the large language models. And we will look at another family of models called the state space models, or SSMs. So these state space models are a very alternative or a very attractive alternative to the autoregressive large language models because of some of the advantages that they would offer over the autoregressive models. Then we will also look at the normalization flow based models. And so on. So this is the broad family of models that we will be looking at. So we'll start with this is the course outline. We'll start with introduction to probabilistic ML. Then we will look at the variational methods, which are latent variable models, the mixture models, mixture densities, variational autoencoders and its variations. We will look at the diffusion models, and for the adversarial family we will look at the generative adversarial networks. We look at the family of autoregressive models, which are transformer based large language models. We will look at state space models and also discuss normalization flow based models. So this is not an exhaustive list of everything that we are going to cover in this course, but broadly this is these are the models that will definitely be covered in this course. And then at the end of the course, we will also look at some of the reinforcement learning methods, such as RLHF and the DPO, PPO, and so on, which are used as the post training methodologies for large language models. So that's the broad plan, the course plan that I have envisaged for this course. So with that, let us start looking at the probabilistic way of approaching the problem of machine learning. So we will look at the probabilistic machine learning. So perhaps before we continue with the further topic, I would encourage all the students taking this course to have the background, or rather acquire the background that is required to take this particular course. So if I have to list the prerequisites, if one has enough background in the probability theory and the random processes, that would serve the student a lot in this particular course, because all the algorithms that we will be looking at in this course will be dealt with from a probabilistic standpoint. So having a strong prerequisite on probability theory and statistics would definitely help the student. The other prerequisite would be if the student also know a bit of classical machine learning, where they understand the way the classical ML algorithms are built, such as the linear models, the linear regression, and the neural networks, and the kernel methods such as SVMs and the graph-based methods, and so on. That would help the student in this particular course. And a bit of programming background, especially in Python language, is much needed, because all the implementations that we will be doing of these algorithms that we study will be based on Python. So even though we will have a couple of initial tutorials on the libraries such as PyTorch, upon which we build this entire course, having some background on the fundamentals of programming would definitely help. So the treatment that we will be taking in this particular course for machine learning will be probabilistic. So I assume that the students that would take this course are already equipped with the fundamentals of the probability theory, and then build the foundations starting from there. So now, what is probabilistic machine learning? The fundamental problem that we encounter in machine learning is that of modeling the uncertainty, right? So the foundational problem that we'll be looking at the entire machine learning would be that we have to model the uncertainty. So what do I mean by modeling the uncertainty? Is that we want to understand the system. You can take the example of understanding the human language as a system. So that's what we do in language models. So now there, understanding the human language, typically whenever you want to model a particular system in engineering, you would go to the physics of the problem, which is the foundations of how the boundary conditions or the systems are built, and then you try to model that system using the known physics or mathematics. An example can be, suppose you want to understand how a particular rigid body moves from point A to point B, then you have to know ideas such as the momentum, acceleration, the position, and so on, and you measure all of them using a physical device, and then build math, which is the Newtonian mechanics that has deterministic math around it, and you can completely specify the trajectory of a particular rigid body that moves from point A to point B. So that is an example of how you deal with problems from the first principles of physics. Now, if you are dealing with problems such as modeling, let's say, human language, or trying to understand what is there in an image, which is a natural scenery, and so on, then there are things that are non-measurable. For instance, the idea of whether some person is present in a particular image is not physical. It cannot be measured. Or another concrete example can be, let's say that you have the problem of classifying whether a given email is spam or not, right? So in that particular situation, the idea of what constitutes a spam and what does not constitute a spam is not something that can be physically measured using instruments, correct? So that has a lot of perceptual association with the ideas. So whenever you have these kinds of situations where you are interested in measuring things that are abstract, or rather quantifying things that are not measurable and abstract, one would resort to statistics or probabilistic way of looking at things, where we model the uncertainty or the non-measurable abstracts. So an example can be, classify a body of text. Classify a body of text as, let's say, spam or not a spam. So now this idea of what constitutes a spam or not is very abstract and non-measurable. So how do we deal with something that is not measurable? So another example is, so given an image, so this can be the first example. The second example is, so let's say that we are given an image. Identify a particular person or an object. Identify a particular person or an object from the image. So for instance, we might be interested in finding out whether one particular person exists in a given image, or if we are looking at, let's say, a clinical image such as an X-ray, we are interested in finding out whether a particular tumor is present in the object. Now, the idea of a person or a particular tumor or another object being present in an image, which is the measurement of the amount of light that a particular surface reflects, is very abstract. So what do I mean by that? You cannot measure whether a tumor is present in an image or not. So there is no physical device to measure measure the presence of a tumor or otherwise in an X-ray. So that is a perceptual idea. So now whenever you have to deal with things which are not measurable but abstracts, what do I mean by an abstract? It is something that cannot be physically measured, or rather which has a perceptual association with it. How do we deal with such a situation is the question. Now it turns out that under these kinds of situations where it is impossible or rather difficult to completely specify a given system using the physics or the first principles, one particular tool that has helped engineers and mathematicians to deal with is to So model these systems via repeated observations. So this is something that has worked. In fact, if you look at the today's landscape of generative models, it is this paradigm that has made everything that you see in today's engineering paradigm around the generative models a possibility. Now, what is the idea here? Okay, let's say that I'm interested in classifying a body of text as spam or not as spam. I don't know what constitutes a spam or not. Okay, but what can I do is I can accumulate hundreds and thousands of body of text. Let's say these are emails. I can accumulate hundreds and thousands of these emails and make an expert label that as spam or not as spam. So now I have a lot of instances of a body of text being a spam or not. Now I use that, which is a collection of multiple objects or multiple scenarios of what I want to build, and use that repeated observations to build a system. Okay, so this is the crux of, or rather we can do the same thing for the second example as well. Let's say that I'm interested in finding out whether a particular object is present in an image or not. Okay, what I would do is that I would collect, or rather I will do a lot of repeated observations where I see an image and I see that particular person, or I take an image where that person is absent. Now I model this idea of presence or absence of a particular person or an object in an image by collecting enormous amounts of observations that I make regarding the system that I'm interested in building. A naive example can be that suppose I'm interested in knowing whether a roll of a particular die turns out to be of a particular number to face, then the entire process of rolling a die and what side that it turned out to be is a function of multiple environmental variables that are not measurable. In that case, what do? That we roll that dice multiple times, okay, and make repeated observations and see if we can model the system or the uncertainty and the abstractness that we have using repeated observations that we have made. So this is the central idea, okay, behind all the probabilistic and statistical methods. This is the probabilistic approach, at least the frequentest way of doing it, where if you are trying to model a system where there are variables that are not physically measurable, then one of the ways to model that system is to try to emulate that system multiple times, and then using those repeated observations, see if you can fit a mathematical observation or a mathematical model to the repeated observations that we have made. So that's the crux of the frequentist way of the probabilistic approach. Now we have to concretize all these ideas. It's a lot of talk. We have to concretize all these ideas. So how do we do it in probability theory? Is that we will start with the set. So let us define. So I'll give you a very gentle and a quick introduction to probabilistic machine learning. So I'm just repeating it again. I am assuming that the students here are conversant with the ideas of probability theory. If you're not, I think I would strongly recommend you to take up a course on probability theory before doing this course, because this course heavily relies on the knowledge of the fundamentals of probability theory and statistics. Now, as I said, in the central crux of probabilistic machine learning is that we model the system that we are dealing with using the ideas of probability theory. So let us look at what are the foundations that go behind the probability theory that we would look at, that we would consider to build the algorithms of generative modeling. Okay, so in probability theory, we start with an experiment, which is also called the random experiment. So there is a random experiment that somebody is conducting. So this random experiment can be uh, tossing a coin, or it can be, let's say, rolling a die, or it can be taking a picture, or writing an email, and so on. So it's the choice of a practitioner or an engineer to look at every systemic design that we have from the lens of probability theory. So every kind of system that we encounter can be modeled as a random experiment. Now this random experiment is conducted several times, is the underlying assumption that we have in probability theory, that we have a random experiment that is conducted multiple times. And what does it give? A random experiment outputs what are known as a set of outcomes. So all the possible outputs of a random possibilities of the random experiment are enumerated in a set called set of outcomes. Okay, and if you take a set denoted as omega, and this set will have all the outcomes that are associated with a random experiment. So example can be that if you are looking at the example of tossing a coin, what we have as outcomes are the usual head and tail as two possible outcomes. There can be another random experiment whose outcomes are, let's say, 1, 2, 3 up to 6. So this is for coin toss, and this is for die roll. Okay, and suppose we are looking at the experiment of taking a picture. The possible outcomes are, let's say that we are looking at taking the picture of human faces, then it's pictures of all possible human faces, all humans. So this can be the set of all the outcomes of the random experiment, or it can be set of all possible texts in the internet, and so on. Okay, so in fact, while we work in practice, right, we assume that there is an underlying random experiment that is being done, and what we get to observe are the outcomes of the that particular random experiment. In fact, we will see later that we will not even have the raw elements of the outcomes of the sample space. We will have something else that we define right now, which is called the random variable. But anyway, so the idea of the idea of a random experiment is that there exists, this random experiment may be conducted by a person or a set of people or the nature. So it is all the systems that we see, or the data that we get, can be looked into as the possible outcomes of this random experiment, and the way we quantify the random experiment is through a set which is called the sample space. So outputs of a set of all possible outcomes is what is called as the sample space, it's denoted with omega. So sample space is a set of all possible outcomes of a random experiment. So please note that, let me just complete this random experiment. So please note that I have not formally defined what a randomness is in this whole discussion. In fact, it is not a well-defined idea. So what randomness is, we assume that it is random. Actually we should put it within the code. It's random because we are not dealing it from the first principles of physics. Rather than that, it does not have any mathematical significance, and this is the only randomness that figures in the entire probability theory. Everything else is well defined and formulated from the measure theoretic principles. So this is the only level of randomness, or so-called randomness, that we deal with. Anyway, so the starting point for all the probabilistic treatment of machine learning is this idea called sample space, which is a set of all possible outcomes of a random experiment. Now we don't stop there. So once we have the sample space, what do we do with it? So sample space, as we saw, is a set. So on this particular sample space, we define what is called as a probability measure. Define probability measure on the sample space omega. Now what do you mean by a probability measure? So I'll not go into the definition of what a measure is, but roughly the idea of measure is that if you are given a set, if I have to quantify the length of a particular set, okay, or rather suppose I have a set and I want to compare two subsets of a particular set, then I'll have to have a metric, okay, where I can measure, quote unquote, measure the size of the subset of a particular set. I'll give you an example. So we all know that we have the set of real numbers, right? And suppose we take two subsets, A and B. Let me write those sets. So the idea of a measure. So a measure is actually a function, let me call that as M. A measure is a function from the subsets of a particular set. So let's call it's from subsets to positive real numbers. So this is the broadest definition of what a measure is, and there can be multiple measures that one can define. We already know the idea of measure from the usual Lebesgue measure that we use. Let me just illustrate that. So what's the idea of a measure is that suppose we have subsets of, consider the set of real numbers and A and B be two subsets of the set of real numbers that we are looking at. So an example can be, you have A is a set between 2 and 4, which is a subset of real numbers, and B is another set between let's say 6 and 16. Okay, now if I'm interested in knowing which of these two sets are bigger, which of these two sets are smaller, so suppose I want to compare the size of A and B. So what do? I have to define something which translates a particular set into a positive real number so that I can compare positive real numbers, right? So that's the idea of a measure. So if you have to compare the size of two sets A and B, we can define a size measure. So define what is called as a size measure as, suppose you have a set A which is a subset of real numbers. So let's say A is defined as closed A and B. Then the definition of the measure of A, let's call that M of A, can be defined as the modulus of the absolute value of difference between B and A. Right? In fact, we know this, right? So this is what the usual the Lebesgue measure that we use, or the length measure. So this quantifies the idea of size or length of a set in if we are considering the subsets of real numbers, right? So now given the sample space, which is a set of all outcomes that we have, so the question is, can we define? So now the question is, how to define a measure that quantifies the idea of uncertainty associated with outcomes. So this is what we are interested in. So we are interested in quantifying and measuring the uncertainty associated with outcomes, because remember our whole goal is to quantify or model a system that has uncertainty in it, and we started by enumerating all the possible outcomes that the system throws at us, and then if we have to proceed further, we'll have to associate a particular measure upon the subsets of the sample space or the outcomes that we have of the experiment, and this measure has to quantify the uncertainty that is associated with each of the outcomes, right? So that's the idea. So to do that, so first we will define what is called as the event space F, which is set of all subsets of omega. So just like we define the Lebesgue measure or the length measure on subsets of R, we'll have to define a measure on the subsets of omega, which is defined as the event space. This is also called as the event space, where an element A, which is a member of this event space, is actually a subset of the sample space omega. Right? You consider any subset of the sample space omega, that becomes an element in the event space. Okay. Now we define what is called as define a measure on the elements of the event space F as follows. So define a measure, call it P, denote it with P. So this is a measure that takes an element from the set of events and maps it to a number between a real number between 0 and 1. So this measure is called the probability measure. So think of it like the idea of size or length. Just like we have the idea of length or size defined upon the subsets of real numbers, you think of it like the size of every element that is a subset of the sample space. Okay, so we look at the outcomes of the experiment, one outcome or multiple outcomes of experiments that we are doing, and associate a number between 0 and 1 on each of these elements of the event space. Okay. Now, any measure should have a particular property, a set of properties. So we assign a set of properties on this particular measure that we define on the probability measure. And some of the I'll not list all the properties, but I'll list a few important properties. Properties of the probability measure is as follows. Now, if we take the first property, is that the probability measure associated with every element of f is always greater than or equal to 0 for every member of the event space. Okay, and the second property is that if we consider the measure of the entire sample space, then it is 1, and the measure associated with a null event is 0. The third property is that if A and B are two elements of the sample space such that the intersection of A and B is null, then the probability measure associated with the union of these two elements is equal to the sum of the individual probability measures. Okay, so these are the properties of the probability measure. So now what's the idea? The idea is that given a particular element of the event space, which is a subset of the sample space, we associate a number between 0 and 1 with each of those events and call it a probability measure. And this has these properties that the probability measure associated with every element in the sample space is always greater than or equal to 0. The least value that it can take is 0. The probability associated with the entire sample space, note that sample space is also an element of f, right? That is equal to 1, and the probability associated with the null event is 0. And if there are two events such that they do not intersect, then the probability of their union is the sum of the individual probabilities. Now, this is a measure that we have defined on the subsets of the sample space. Now, how do we want to interpret this measure is left to us, in the sense that just like we see, whenever we look at the Lebesgue measure, we interpret this Lebesgue measure as the length of a particular subset, isn't it? So if you take a subset of A and B, a subset of real numbers which is A, B, closed A, B, then this Lebesgue measure that we defined can be interpreted as the size or length of the set, isn't it? Similarly, probability measure is a mathematical construct in the sense that it's simply a function from the subsets of the sample space to close 0, 1. Now it is for us to interpret whatever it means. So remember, what was our goal? Our goal was to define a measure that quantifies the idea of uncertainty associated with the outcomes. Now we just defined a measure which is between 0 and 1. The reason it is defined between 0 and 1 is because we want to interpret that as something that is quantifying uncertainty. Right? So if the probability measure associated with a particular event is 1, then we interpret that as an event that has 0 uncertainty, in the sense that it is a certain event. And that is why the probability of the sample space is 1, in the sense that we are saying the uncertainty associated with sample space is 0, or rather, because uncertainty is what we are trying to quantify with P. It is the uncertainty associated with the sample space is 0, or the probability of that happening is 1, because something will always come out if you do the random experiment, right? I mean, we are saying what is the uncertainty associated with the sample space, we would say that it's 0. Similarly, the uncertainty associated with the null event is 0 because there is nothing that you can be certain about the null event, right? And also here we are saying the uncertainty associated with the union of two events is equal to the sum of the individual uncertainties as long as these two events do not intersect. Okay, so now the way I just presented, looks like the probability measure is the inverse of the uncertainty. Of course, it's the inverse of uncertainty, and that's why probability measures are also interpreted as the likelihood, or the likelihood with which a particular given event would happen, right? So one can interpret this probability measure as the metric that would quantify the uncertainty associated with every element which is every element of the sample space, okay, which is the outcome of a particular experiment. Okay, so now what did we land on to? We had, so given a random experiment, given that we are conducting a random experiment, there is a random experiment, we ended up getting a triplet. There is a triplet, a mathematical triplet that we constructed, which is set of sample spaces and set of subset of the sample space called the event space, and we have a measure that we have defined on top of this. This triplet is what is referred to as the probability triplet. In fact, this is the starting point of all the machine learning that we would do, that we start by assuming that there exists a random experiment whose outcomes are enumerated in the set called the sample space, and we have a set of subset of the sample space called the event space, and we define a measure called the probability measure, which has the properties that we just discussed, and defined on the subset of the outcomes of the sample space. So okay, this is the sample space, and this is the event space, and this is the probability measure. So I've still not told you what's the practical relevance of defining the sample space, event space, and probability measure. We'll get to that in a while. But remember, what's our goal? Our goal is to model systems with unknown measurements, or rather abstract measurements, and we want to study the behavior of those systems. What are some of the concrete use cases or the questions that we will be asking while modeling these systems is something that we will see later in this course. One example can be that can we emulate that particular system, which is what the question that we will ask in generative models. That is one question. The other question is that can we probe the system and see what sort of a behavior that the system would describe, or system would demonstrate if it is presented with a particular type of an input, and so on. We will ask some of those questions as we move on in this course. Mostly the emulation question is what we will be asking, because we are looking at the generative part of it. But yeah, so the idea is, the summary so far is that if we are given systems that have abstract and non-measurable parameters, one of the best ways to quantify that is to model it using repeated observations. Now, how do we do that? Is by assuming that we have a random experiment. Okay, the system is the system gives out the outcomes. System is conducting random experiments, and it gives out some outcomes, and these outcomes are enumerated in a set called the sample space, and we define a measure called the probability measure on this particular set that would quantify how certain or how likely a particular outcome of this particular sample spaces, okay, or random experiment is. Okay, so from there we will move on. See, what will happen is, in practice, we'll have to now come to the practical world. So oftentimes, or most of the times in practice, one would not have access to the probability triplet, which is right. We don't get to see what the sample space is. We'll not know what the outcomes are, and of course we will not know what the underlying probability measure is. Now, to do that, but what we will have is some surrogate of the random experiment, which is a measurable thing. Let me tell you what I mean. So if you take the example of let's say gathering an X-ray or taking an X-ray image as the random experiment. So do we have the outcome of this taking an X-ray as a random experiment? We don't, because it has abstracts. Now you can still say that, oh, we do measure an X-ray image, and what we have is a measurement that we see as an X-ray image. But the counter argument to that is that what we have is not the outcome of the sample space, but a surrogate on top of it. What do I mean by that? This entire process of a person getting in front of an X-ray machine and the radiations being shined on that particular person, and you measure the X-ray, that is the X-ray radiations that are passing through that particular object, and capturing it on a particular screen and converting that into something that can be read through computers. If you take that entire process as the random experiment, so we don't have the outcome of it, but what we actually have is the final set of numbers that we read on X-ray, that we read as an X-ray image in a computer. Okay, so which means that what we have as the outcome is a surrogate. Let me give you another example. If you take the example of creating a textual sentence and constructing that to be a spam. Let's say that somebody is typing a paragraph that would constitute as a spam. Now, what would be the elements of the sample space in that case would be that somebody thinking that he or she would create a spam, and then constructing a set of words that they would type out, and this entire process of typing something out constitutes the random experiment. What do we get to observe are a set of Unicode characters that we measure in our computers, which is not the same as the outcome of the random experiment, but a surrogate on the sample space. So what do I mean by that is that we would not have access to the probability triplet. We get to measure a surrogate of the elements of the sample space. So what are these surrogates? These are actual measurements that we do. The actual measurements that we get to work with are the surrogates that I'm talking about. So now we want another mathematical tooling that would capture this idea that we don't have the elements of the sample space themselves, but what we have are surrogates of the sample space. So now we define another function on omega to describe the surrogate or the measurement that we have. What do we mean by that? We start with omega and define a function on top of this omega, okay, which maps it into real numbers. So what we actually finally get to measure are real numbers, isn't it? Suppose we are looking at an image. The elements of those image are real numbers. So finally what we work with are not the elements of the sample space, but we work on a surrogate of the sample space. And what do I mean by surrogate? It's a representative of the elements of the sample space, which are real numbers. So finally we get to work with real numbers, which we call our data. It can be an image or a text or a speech signal or anything. And these are not elements of sample space, irrespective of the random experiment that we are conducting, or that the nature is conducting. Finally, what we get to work with are real numbers, which are our measurements, which is our data. Now we need a mathematical construct that would translate the elements of the sample space onto the real numbers that we work with. Okay, and that mathematical construct is a function that takes the elements of the sample space and maps it to real numbers, and this function is what is referred to as the random variable. This is random variable. So I keep saying this multiple times, random variable is such a misnomer that random variable is neither random nor a variable, right? I mean, it's actually a deterministic function that we look at. It's actually a function. A random variable is a function from sample space onto real numbers. Now, in general, it can be a function from the sample space to a d-dimensional Euclidean space or d-dimensional real vector, which is that where d is any arbitrary positive real number. So, what does this random variable give us? This random variable takes the elements of the sample space which are abstract, which we do not get to observe, and maps it to a real vector that we actually observe in practice, which we work with. An image now will be an element from a d-dimensional real space, right? So that element from the d-dimensional real space now can be seen as an element from the sample space being transformed into a d-dimensional real number under this function called random variable. Okay, so now once we have the a function that we have defined on the set omega, what happens to the probability triplet? So once a function random variable, a function which is called the random variable. So again, I keep saying this because people generally mistake this idea of random variable. They think that it's a variable. It's actually not a variable. It's a function that we define on sample space. So once a function called random variable is defined on omega, the probability triplet that we talked about also gets transformed. So what is meant by that is that we start with the probability triplet omega and the event space f and the probability measure p, and then we define a function on top of omega. Once we do that, omega gets translated into a d-dimensional real space. Okay, and then the event space gets translated to something called Borel sigma algebra, which is I'll just talk about it, and the probability measure gets translated into something called a distribution function. Okay, so let us define all of these. So of course we know that x is a function that is anyway defined from omega to rd. This we know. Okay, so this is converting each element from the sample space to an element in rd, which is a d-dimensional real vector. So given an element in the sample space, the random variable as a function will give you a vector in rd. Okay, so what is b? The sigma algebra or the Borel sigma algebra is now, so now f used to be the subsets of omega, correct? So f was the subset of omega, and therefore the Borel sigma algebra b is a subsets of Rd. So if you take the real numbers and take the subsets of the real numbers, then you get the sigma algebra B. And what happens to the probability measure that we defined? So P gets transformed into something called a distribution function that I talked about. So what is a distribution function? Let's define that. A distribution function, okay, defined at a particular value x. Now please note the notation here that I write script p for denoting the distribution function, and this x, which is the subscript on the distribution function, tells us that this is the random variable that we are talking about. This is the function which is called the random variable. I mean I cannot emphasize this enough. A random variable is a function. Okay, it's just a bad nomenclature calling it a random variable. It's actually a function. So this the distribution function is something that is defined via a particular random variable x, and it is getting evaluated at a point x. So please note that this x and this x is different. Maybe let me just write it using a different notation here. Let me use small x to define that I am measuring it. So this is, I am measuring this function, evaluating this function at this small x, and this is defined under the random variable capital X. So what is this defined as? This is defined as the probability. Okay. So note that the probability measure is always defined. By definition, probability measure operates on the elements of F, which is the event space. Okay. So now whatever goes as an input to the probability measure has to be an element of the event space. Okay. So now this probability, it's the probability of an event A. What is that event? It is that event which gets mapped to a particular set, which is minus infinity to x, which is the small x, under the random variable x. What do I mean by this? So it looks complicated, but it's not. Let's say that I have a random variable x, okay, that takes an element of omega and maps it to real numbers r. Okay, we are looking at the case where the domain or codomain of the range space of the random variable as a function is real numbers. If we have a case like that, now imagine a set A, okay, which is an element of the sample space, and this set gets mapped to a subset in R under the random variable, isn't it? So whenever we take a random variable, which is a function which takes an element of the sample space and maps it to real numbers, every subset of omega, which is an element of F, gets mapped to some subset of R or some element in the sigma algebra that we talked about. Okay. Now every subset of F gets mapped to a subset of R under the random variable x because it's a function. Now suppose this set A, which is an element of the event space, gets mapped to this particular subset, which is open minus infinity to closed x under x. Now what am I saying is that if you take a subset of the sample space or an element of the event space such that it gets mapped to this particular subset of R under the random variable, that is possible, right? So what happens is that every element in the sample space is now getting mapped to a real number. Now if you take a subset of the sample space, which is an element of the event space, that also gets mapped to some subset in R under the random variable. Now suppose there exists a set in F such that it gets mapped to this particular subset of R. So this thing is a subset of R, isn't it? So this particular subset is this set is a subset of R. If that gets mapped to that particular subset, then the probability distribution function under the random variable evaluated at this small x. Please note that the small x here, which is an argument under the distribution function, is same as this x that we are talking about. Now, this is defined as the probability measure, okay, of set A. What is the set A? Set A is simply that subset, okay, which gets mapped to this particular subset under the random variable. So what we are saying is that what is this x inverse? X inverse is the inverse image. So whenever you define a function, you can always define an inverse image of that function. So take this function random variable, okay, and take the inverse image. So what does the inverse image of a random variable do? Well, while random variable takes an element of the sample space and maps it to R, the inverse image of this function takes an element of R and maps it to omega, isn't it? That's the inverse image. So therefore, you consider the inverse image of this particular subset of R, okay, that gets mapped to some subset in omega, which is an element of F. You consider the probability of that particular set, which is well defined because we define the probability measure on the elements of the subsets of the omega, which are the elements of the event space. Okay, so this probability becomes a well defined measure. So that probability is what we refer to as the probability distribution function. So this is the probability distribution function that we evaluate at x. So let me just write it completely so that the picture is clear now. The probability distribution function under a random variable x evaluated at small x. So this is how one should read this. So now this is what we denote as px evaluated at x. Okay. So this is how is this read? This is read as the probability distribution function, okay, under the random variable x evaluated at small x. This is how one reads that. So this is equal to is the probability of the event A, okay, that probability of event A that gets mapped to a particular subset, mapped to this particular subset under the random variable x, right? So probability distribution function of a random variable evaluated at x is equal to the probability of a particular subset A, okay, that gets mapped to minus infinity to x under the random variable. How do we write that? Write that as the inverse image. So if you take the inverse image of the random variable of the set minus infinity to x, then whatever subset that you get of omega, compute the probability of that particular subset. That is the distribution function evaluated at x. Okay, see, it looks like a very complicated definition, but it is defined in this particular way because the idea is if you consider the probability of this particular subsets under R, then the probability associated with any subsets can be computed. Okay, so it is with this idea that these particular subsets of the real numbers are considered. Okay, so now what happened finally is that we started with this particular triplet, which is omega, f and p. We don't have access to this, and then this gets transformed or pushed forward into another set, which is R, real numbers, and then we have the subsets of real numbers and the probability distribution function. Okay, now what happens in practice is this is not accessible, right? But this is what we measure and work with. We measure this and work with this. Not accessible and abstract. So this is the non-accessible and abstract part of it. So we assume that every system that we are modeling has this framework under it, that there is a random experiment that is being conducted and there is a subset of the set of all the outcomes of the random experiment, and we define a probability measure on top of it, and then we don't have access to it. To ensure that we are actually working with something that we measure, we define what is called as a random variable. So this function is the random variable which is a function as I just talked about. So this is a random variable. We work with a random variable and convert the probability triplet omega fp into real numbers, the Poral sigma algebra, and the distribution function. Now you will see in the upcoming sessions of this course that the entire problem in generative modeling is to estimate the underlying probability distribution function. So if you estimate the distribution function, it is equivalent to estimating the underlying probability measure, and this is what we had to do from the beginning, right? I said that our whole goal is to quantify the uncertainty that is associated with the system, and this is the way we quantify the probability measure, is the way we quantify the uncertainty. And the whole problem in machine learning, as we will see later, is that we want to estimate the probability distribution function. Okay, so with this I will conclude today's session.